In every series solution thus far, we've always been around the point x naught equals 0. So let's take a look at the techniques and an example to where we have an ordinary point that's not about 0. So this time we're going to find the solution, a series solution, to y double prime minus xy equals 0, and we're going to go about the point x sub naught equals negative 2. So remember our form. We're going to start by saying our general series that we'd like to be able to have is going to be series n equals 0 to infinity c sub n, and usually it's x to the n, but this time it's going to be x minus a minus 2 to the nth power. Okay, or that just becomes x plus 2, obviously. And so that's really the only difference in the setup. Now, there are going to be some algebraic differences. So we're going to say y equals this. We need y double prime, but to get to y double prime, we need y prime. So y prime is going to be shifting the index n equals 1 to infinity, c sub n, n, x plus 2 to the n minus 1. And then y double prime is going to be series n equals 2 to infinity, c sub n, n, n minus 1, x plus 2 to the n plus 2 power. At this point, we're going to substitute, and everything's normal. So we're going to have the series that we just got. Remember, our original differential that we're looking at is y double prime. So it's going to be series n equals 2 to infinity, c sub n, n, n minus 1, x plus 2 to the n plus 2, or n minus 2, excuse me. This should be an n minus 2. And this should be x plus 2. Minus x times the original series. All right, so we have xy, and the original series was series n equals 0 to infinity, c sub n, x plus 2 to the nth power equals 0. Alright, now here's the sneaky trick that we're going to have to do. Usually what we do is we take the x and we just distribute it onto the inside. And that's one of the beautiful things about the series, is that allows us to just switch the exponent. However, we can't do that because we don't have x minus or x plus 2. So here's what we're going to do. We're going to do a trick that a lot of times we see in mathematics, where if we don't have something, we're going to add and subtract to be able to get to what we need. So we're going to rewrite this as series n equals 2 to infinity, c sub n, n, n minus 1, x plus 2 to the n minus 2, minus, and here's what we're going to do. We're going to have x, and then instead of just x, it's going to be x plus 2 minus 2. And we do that so that way we can have an x plus 2 so that we can distribute into the series. All right, now we're still going to have the series n equals 0 to infinity. I'm just going to continue on the next line. C sub n, x plus 2 to the nth power equals 0. And what we're going to do is we're going to distribute. So we are going to take this quantity of x plus 2, we're going to distribute it to a series, and then we're also going to make a third series and distribute that negative 2. And remember, it's the opposite of negative 2. So eventually it's going to turn into a positive. Okay, so let's just do some distribution here. And again, this is the common technique we need to be able to solve these series about other points than 0. So now we end up with series n equals 2 to infinity, c sub n, n, n minus 1, x plus 2 to the n minus 2. We're going to distribute the x plus 2, so that's going to be minus quantity x plus 2, series n equals 0 to infinity, c sub n, quantity x plus 2 to the nth power. And then now we're going to distribute that negative 2, but remember it's the opposite of negative 2. So it's going to end up being plus 2 series, n equals 0 to infinity, c sub n x plus 2 to the n equals 0. All right. Now at this point, we're ready to go through and distribute that x plus 2 back in. All right, so now we're going to distribute the x plus 2 into this factor of x plus 2, and then we can start worrying about shifting the indexes. All right, so one last time that we're going to rewrite this before we switch into k's. N equals 2 to infinity, c sub n, n minus 1, x plus 2 to the n minus 2, minus series n equals 0 to infinity, c sub n, x plus 2 to the n plus 1, because we just substituted n plus 1 and we distributed that back in. All right, so that's a distribution of x plus 2 back in there, and then plus 2 series n equals 0 to infinity, c sub n x plus 2 to the n equals 0. All right. So, good news is we've gotten rid of all the variable coefficients out in front. Bad news is that now we have to do the change of index. And you might recall from previous examples, what we like to do is we like to pick on, and we like to leave the biggest index, and we like to pick on the smaller. So we're going to pick on these two, and we're going to try to make these two look like n plus 1. All right, so that way we always want to try to make it look like the biggest one rather than going backwards. All right, so to do that, in the first series, we're going to let n be equal to k plus 3, because k plus 3 minus 2 is going to give us k plus 1. In this series, we're going to let n equals k. And then right here in the third series, we're going to let n be equal to k plus 1. Now keep in mind that's going to shift the indexes. All right, so that means that we're going to have n minus 3 equals k. So n minus 3 is going to be equal to k, and then n minus 1 for that third series is going to be equal to k. All right, so we're going to have a little bit of shifting of the indexes, just to kind of make sure we know which step is which. Right? So by substitution, we're going to end up with series. We're going to subtract 3, and we're going to have k equals negative 1 to infinity, c sub k plus 3, k plus 3, k plus 2, x plus 2, and then k plus 1. So we substitute k plus 3 back in for all of the n's. All right, just like we have in all the other examples. So it'll be k plus 1. The second series stays minus series k equals 0 to infinity, c sub k, x plus 2 to the k plus 1. Right, that's good because we want a k plus 1. And then finally we're going to substitute k plus 1 back in. So we have 2 series. We're going to subtract 1 from n. So it's going to be k equals minus 1 to infinity. And we're going to get c sub k plus 1. And then quantity x plus 2 to the k plus 1. And all that equals 0. All right. At this point, again, good news is now we have all the exponents affixed to the x plus 2 quantity binomial equal to k plus 1. That's good news. The bad news is we can't yet factor out the series because we notice that we have a couple series of k equals minus 1, and then we have this series of k equals 0. So remember what we do is we split off whatever we possibly need to. And remember, we always start with the smaller ones and build up. The good news is we only have to split off 2 terms. So we're going to split off k equals negative 1 in the first series, and we're going to split off k equals negative 1 in the third series. And if we do that, so we're just going to let k equal negative 1 in that first series. And if we do that, we get c sub 2 times 2 times 1. And then this just becomes x plus 2 to the 0. And then we're going to split off k equals negative 1 in the first series, or the third series, excuse me. And that's going to turn into 2, so we have the 2 out front. C sub 0, x plus 2 to the 0 power. Now, we're going to go ahead and rewrite all the series one last time before factoring, but now all of the lower level, or the lower bounds of the index are all going to be 0. All right, so we're going to have plus series k equals 0 to infinity, c sub k plus 3, k plus 3, k plus 2, x plus 2 to the k plus 1 minus series k equals 0 to infinity, c sub k, x plus 2 to the k plus 1, and then finally plus 2 series k equals 0 to infinity, c sub k plus 1, x plus 2 to the k plus 1. And all that equals 0. Alright, so mercifully, we've gotten to the point now where now we can start working on the series as well as those coefficients. Alright, so in this step, what we're going to do is we're going to simplify these undetermined coefficients. So we know that this is just going to be 1. We know that x plus 2 just goes to 1 for both of those. So we're going to get 2c2 plus 2c naught. And then we're also going to factor out the series k equals 0 to infinity. We're going to also factor out the x plus 2 to the k plus 1. And that's going to leave us with just those coefficients so we can get our generating function. So we're going to factor out that x plus 2 to the k plus 1. And we are going to be left with c sub k plus 3 times k plus 3, k plus 2, plus just c sub k, or minus, excuse me, because of the minus that's right here. All right, so almost made a copy error there. All right, so let's erase that. And then finally plus 2 of the series, or no series, c sub k plus 1, and that should do it. Equals 0. Alright. So what does this give us? Alright, so it gives us a lot of good stuff at this point. Alright, so what we know is, let's pick on these coefficients. Right? We know that these two constants have to add up to 0. So we know that 2c2 plus 2c naught has to be equal to 0. Or, in other words, c2 equals negative c0. And we're going to hold on to that. Right? That's important because as we go along, we have to make sure that when we get our generating function, that is true. If that's not true, then we made an error somewhere in here. Right? Another thing that we know right away is that the only way for this sum to be equal to 0 is if you just keep adding zeros. All right? And the only solution to that is going to be when x is equal to negative 2. And that's not really necessarily surprising because that's what our point is going to be centered about, or that's what our series is going to be centered about. We know that's the trivial solution. All right? And then finally, the one that we really care about is the one with the c sub k's. All right, so we have this c sub k plus 3, k plus 3, k plus 2. And then we have minus c sub k plus 2c sub k plus 1 equals 0. And what we're going to do is we're going to solve that for c sub k plus 3. So the goal is always solve it for the highest possible term, all right, and the one with the highest order, so that way we can get that term in terms of the previous. That's what we do with all our recurrence relations, all right? So if we solve this for c sub k plus 3, that's going to be equal to c sub k minus 2c sub k plus 1s, and then we're going to divide that by k plus 3, k plus 2. All right. And we're going to have to stop there because there's nothing else that we can really do at this point to be able to simplify it. So this is our generating function. And we'll stop the video here so that way we can go through our method of iteration in the next video to be able to guess a solution or to be able to get to our polynomial, and then we can write the solution out in terms of a polynomial.